Hey, BC Calculus, watch Mr. Canfield relearn power series. Earlier, we introduced the idea of approximating functions by Mclaren and Taylor polynomials. For example, we showed the fx equal to fx. So here's the Mclaren polynomials. Remember, Mclaren meant that it's a Taylor series where the center is at 0. And remember, Taylor series, they would, instead of having x's for all the terms, they had x minus c for all the terms, where c was the center. Mclaren's center was 0, x minus 0 made it look simpler. I realize this is a different formula, but it had the x minus c thing, so it's good to. So now that we know things about infinite series, we're going to look at infinite polynomials. So there's a specific infinite series called the power series. Power series for e to the x is 1 plus x squared over 2 factorial. It's this. This is the power series. And this power series converges for all real numbers x, allowing calculators or computers to calculate e to the k, where k is a constant, to extreme accuracy. So basically what happens is, we talked about this. We talked about this idea of the more terms you get, the better an approximation you get. And so these polynomials, they just fit into something called power series. And power series is a specific kind of Taylor and Mclaren polynomials. So first thing, we want to make sure we can actually identify a power series. So a power series is a bunch of coefficients, and it goes x to the 0, x to the 1, x to the 2, x to the 3, x to the 4. Like, it's got x's in here. But look at this. The x is a variable, and a is a coefficient. So we're mushing the last two things we learned. We learned these infinite series with all these different n's and stuff like that. That's what we're doing now. And now we're mushing polynomials into those series. So let's look at this series here. So, you know what? Since, you heard me a minute at the beginning, I'm a little rusty. I want to make sure that I don't make any dopey mistakes. Let me pull up my answers. All right. So when we're plugging in n's here, we're not plugging in things to x. So it's going to be x to the 0 over 0 plus 1 factorial plus x to the 1 over 1 plus 1 factorial plus x to the 2 over 2 plus 1 factorial, which is 3. So is this a power series? Yes, this is a power series. The way how you know is, well, x to 0 is 1, that's 1. So this is 1 plus 1 over 2 factorial x to the 1. That's a coefficient. Plus 1 over 3 factorial x to the 2. That's a coefficient. So it winds up being a coefficient times x to a power. And that x power keeps on increasing as we go. So like if we look at this one, that's going to give us a coefficient, and this is going to give us, this time it's going to be x minus 1, but it's still going to be to an increasing power. So if we look at our terms of this, and I plug in 0, well, that's going to be 1, and that's going to be x minus 1. This is all just 1. And then when I plug in 1, I get negative 1 here, so it's going to be minus x minus 1 to the 1. Then plug in 2, that's positive x minus 1 to the 2. X minus 1 to the 3, x minus 1 to the 4, and so on and so forth. This is a power series, and its center is at 1. Is this a power series? N over x to the n. So this is going to be 0 over x to the 0, so it's going to be 1 plus 1 over x plus 2 over x squared plus 3 over x to the fourth. And no, this is not a power series. Power series is a polynomial. This is not a polynomial. We've got x in the denominator. Okay. So the domain of a power series is the set of all x for which the power series converges. So like if we look at this example here, if x is 1, so we have this big polynomial that goes forever. If we plug in 1 for x, then we get 1 plus 1 over 2 factorial plus 1 over 3 factorial, blah, 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 plus 1 over n plus 1 factorial. And you can do the ratio test on this, but it's 1 over n factorial, essentially, and n factorial is on the bottom is a convergent thing. Likewise, this, if x was equal to 1 in this example, wait, in the second example above, x is equal to 1 is not in the domain of this, as 1 plus, wait, 1 is fine. 1 minus 1 is 0. Oh, this is a typo. This is supposed to say, let's say 0 here. If I plug in 0 for x, then it's negative 1 to the n times negative 1 to the n. Wait, this is always positive. I think he means to say 2. I checked here and then that and that. Oh, actually, okay, we can say, but in our case, so he fixed it on his computer in the computerized version and he used 0. If we use 2 here, then we have negative 1 to the n times 2 minus 1 is 2, so times 1 to the n. So that gives us 1 negative 1 plus 1 minus 1 plus 1, and that is a divergent situation, right? It's not converging to anything. It's not flowing off to infinity, but it's not landing anywhere. Okay. Is it all coming back to you yet? No, it's all coming back to me. What interests us is what values of x make the power series converge, meaning the series reaches a finite limit. There are 3 possibilities for values of x for which the power series converge. At a single point C, meaning there's only one x value that actually works. Every other x value makes it a divergent series. An interval around the center. So at some point C, which is usually going to be our center, an interval around our center, or you can pick anything you want for x and it's fine. So if we look at this one, oh, excuse me, the center is 0, right? If we plug in the center 0, we get, and we add these up forever, well, all the tops turn into zeros, meaning all of these turn into 0. So 1 plus 0 plus 0 plus 0 plus 0 forever is 1. So it converges when x is equal to 0. We haven't said where else this converges. We're just saying it does converge there. In example 2, let's see if it converges at its center 1. Let's plug in 1. Then it's just negative 1 when we plug in 0. And then it's 0 the rest of the way, so it's 1. So the center is good. So a lot of times the center is good. And I don't know if I said this out loud already, but it goes the same way in each direction from the center, and we call that the radius of convergence. So let's find the radius of convergence of this thing. 1 plus 2x plus 6x squared plus 24x cubed plus ... This is clearly a power series. Anytime somebody in math uses the word clearly, I get offended. Have you noticed? I'm like, well, what if it's not clear for everybody? Like me. No, yeah, so this was a power series. And its center, remember the center comes from like, 1 was the center for this, right? So this time the center is 0. If I plug in 0 for x, it turns out it's just 1. It's just 1. Everything else goes away. So it is convergent at 0, but does it converge anywhere else? And the way that we do this, does it converge anywhere else? We generally just use the ratio test for this. So if I use the ratio test here, and I look at the n plus 1 version on top, that's going to be n plus 2 factorial, and then that's x to the n plus 1, and then the regular version on the bottom. Well, so with the n plus 2 factorial and the n plus 1 factorial, everything's going to cancel except for n plus 2 on the top. And then here with the x to the n plus 1 and the x to the n, everything cancels except for just an x on the top. And we know that ratio test converges when this is less than 1. If it's greater than 1, it fails. So we are trying to find when is this going to be less than 1 as n goes off to infinity. Oh dear. Oh dear. Wait. We're trying to find what numbers, what values of x can I plug in here that will, when n goes to infinity, oh no, this is going to be infinity no matter what, times x. So infinity times x is less than 1. We unfortunately do not have any number that makes that work. Except for 0, right? Because 0 worked earlier, and 0 times each of those values individually will tank it, it'll make it 0. So therefore, we can't do anything about this. So we would say its radius of convergence is 0, and the only place it converges is at its center, C, or in this case, 0. So let's find the radius of convergence of this one here. So we got our terms. So let's try the center first. If we try the center, didn't we missed a term here, right? Because if I plug in, oh, it says n equals 1. Okay, we're starting at 1. So we got this. Find the radius of convergence. Okay. Does it converge at the center? Plug in zeros. Yes, it converges at the center. So let's see. We know it converges at the center. Now we just need to check and see, does it converge anywhere else? So let's do the ratio test. So we'll do -1 to the n plus 2 x to the n plus 1 all over n plus 1 factorial, and then we will divide it, which means multiply by the reciprocal of the original. So -1 to the n plus 2 over -1 to the n plus 1, all those are going to cancel. We're going to have a -1 on top. But if you recall, ratio test actually uses absolute value bars, and those are going to be important here. And we're actually taking the limit as n goes to infinity. Like, that's something that's actually happening here. Let's see, x to the n plus 1 and x to the n cancel. There's just an x on top. And then the n factorial and the n plus 1 factorial, everything's going to cancel except for the n plus 1, leaving us with, and we want this to be less than 1, remember. Limit as n goes to infinity, yep. So the -1, we can, let's just leave it there. -x over n plus 1. So let's say you're not sure how to solve this. Well, that's what I'm here for. That's the limit as n goes to infinity, right? So we're eventually going to be plugging in infinity for n. If you do that, this is essentially, sorry about that. If you're plugging in infinity here, it's going to be negative x over infinity. And we're trying to find out what values of x make that less than 1. Well, this is always going to be 0, which is always less than 1, no matter what we plug in for x. Infinity is not a number, remember. So that means that we can plug in any number we want for x. So the radius of convergence, r, we'd say is infinity. And it's convergent for all reals. All right, let's look at another one. Let's find this radius of convergence, 4 times x minus 2 to the n. And you might be thinking that this is going to have some issues. Getting ahead of myself. Okay, so let's see. Test our center 0. Just kidding. What's our center here? It's not 0. It is 2. Plug in 2. What do you get? Gone, 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 gone. Oh, it adds up to 4 exactly. So 2 is good. Now we just need to check on either side of 2, essentially doing this. Let's see. I'm going to do the ratio test again. Let me just make sure that ratio test is the right thing to do here. What? No, I'm doing the ratio test. Okay, so it's 4 x minus 2 to the n plus 1 over 4 x minus 2 to the n. I'm trying to find out when is this less than 1. Cancel, cancel. We get, oh, the 4's cancel, and we just get x minus 2, absolute value of it needs to be less than 1. Wait, the n's are gone. So we just need to find out what values of x make this work. That's pretty sweet. If you don't know how to solve an absolute value like this, the simple way you just do that. You take this inequality symbol, you keep it going the same direction, put it over there, and then put the opposite number over there. If that doesn't make sense and you want it to make more sense to you, you can say, well, I know that x minus 2 is less than 1. I also know that the complete opposite of this, negative x minus 2, is less than 1. And you can solve both of those independently. But this does them together at the same time. So we'll add 2 to both sides, all 3 sides actually. We get 1 is less than x, which is less than 3. So x is between 1 and 3. This is our interval of convergence. But our radius, what's our radius of convergence? Well, here's our center, here's 3, and here's 1. So our radius of convergence is not this whole distance. The radius is here. So the radius is 1. So basically what happens is you go 1 away from your center in either direction and you still get a convergent series. I'll tell you right now, I don't know the significance of this. I am almost positive that this stuff is really, really important with real-world engineering stuff, physics and things like that, and complicated things that help make things work right. I'm pretty sure that it's useful there. I just don't know what it is. I know how to do it though. So let's find the interval and radius of convergence for this one. He's always obsessed with writing the first few terms. I don't feel like it. So let's look at the n+1th version. That's going to be, 2n. Now be careful. That's what the n+1th version of that is. So I actually need to do some algebra here and figure this out. So that's 2n plus 2 minus 1. So it's 2n plus 1. Okay. So on the top, we've got x over 5 to the 2n plus 1. On the bottom, we've got x over 5 to the 2n minus 1. So what's the difference there? We just subtract those exponents. What's 2n plus 1 minus 2n minus 1? Be careful, right? So 2n plus 1 minus 2n plus 1. This is 2. The difference here is 2. So we want x over 5 to the 2 to be less than 1. The absolute value bars are supposed to be there. They don't matter because we're squaring it, right? So we got x squared over 25 is less than 1. So in this case, you might already know the answer, right? Multiply both sides by 25, get negative 25. Oh, yeah, that when we take the square root, it doesn't really work, right? Yeah, so our old tactics don't 100% work here, but hopefully you see that it's negative 5 to 5. Because 5 is 25, so 25 over 25 is 1. And then if we did negative 5, that would also work. And then anything more than 5, it starts to break, because 36 over 25, like, it starts to fail. So we'd say negative 5 to 5, and we could even do it that way. Like on this last one, we could have said 1 to 3 like that. That's our interval of convergence. And then what's our radius then? Right? So we also have to figure out the endpoints. And this is kind of the last little bit for power series and radius of convergence and so on and so forth and stuff. And I did not manage my time well. I need to do this in the next video. Hope this was helpful. I'll see you next time. I need to stop saying that. People need to stop saying, I'll see you next time. I do not see you right now. Does he take things literally? Does he take things too literally? Oh, yeah. I may always get annoyed when I'm watching a video and someone's like, I'll see you next time. I'm like, you've never seen me in your life. Oh, dear. I'll see you next time.